Hello, I am Gabriele Trivigno and I'm going to present our paper, The Unreasonable Effectiveness of Pre-trained Features for Camera Pose Refinement. Our paper focuses on the problem of visual localization, which aims to estimate position and rotation of a camera in a given scene, where a map of the environment is available, being constructed using a database of images of the area of interest. The pose is then typically retrieved by establishing correspondences between the query image and the map. Structure-based methods represent the state of the art, and their typical pipeline involves an offline step where the SFM model, if available, needs to be retriangulated with local features of choice, and global descriptors of the images need to be computed. Then when a new query arrives, first its top k candidates in the database need to be found via retrieval, their features need to be matched in 2D, and matches need to be lifted to 2D, 3D using the point cloud. And finally, the pose can be estimated using a solver. A related line of research is that of pose refinement, where given an initial hypothesis of the pose, the goal is to further refine its accuracy. Recent methods follow a learnable approach, where a neural network needs to train specific features for refinement or implicit representations, as in the case of scene coordinate regressors. Alternatively, methods based on implicit descriptor field need to be trained per scene, and these methods then localize by aligning the rendered features or images via gradient-based optimization or iterative matching. A notable example is Pixlock, which trains a feature extractor on projected points from SFM point clouds to be robust to illumination and viewpoint changes. At test time, at each step, features of 3D points are projected into the query using the current pose estimate, and direct alignment is performed in feature metric space to refine the pose. While effective, these methods share some limitations, and we question the need to train dedicated features for pose refinement. We observe that if a renderable representation of the scene is available, generic pre-trained features are already suitable to evaluate the alignment of the query to the rendered images. To this end, we propose a refinement algorithm based on a render and compare approach, where a particle filter is used to sample candidates to be rendered at each step. This is an overview of our method. Starting from an initial hypothesis, Monte Carlo sampling is used to generate new pose hypotheses, which are then rendered. The similarity of the candidates to the query is evaluated using a pixel-wise dense comparison of generic pre-trained features. This ranking of the candidates can then be used to update the current pose estimate and generate new samples. Additionally, we adopt a coarse-to-fine strategy to exploit the natural hierarchy of deep features, where shallower layers can discern fine-grained details at higher resolutions. We show that the well-known capability of deep networks to estimate perceptual similarity extends to pose similarity as well, and that the sensitivity to pose differences is higher at shallower layers. Additionally, this property holds across different rendering domains, which depend on the available scene representation. Our optimization converges regardless of the features of choice, and while simple ImageNet features already perform well, we show that this property holds across different kinds of features, and that even with a simple AlexNet architecture, it is possible to achieve satisfying results. On the benchmark of Cambridge landmarks, we compare with pose regressors and other refinement methods that learn specific features, often per scene, and find that our method is able to match or surpass their accuracy. We also test our method on the large-scale benchmark of Aachen, where we compare with Pixlock and show that we are also able to outperform their approach. We also show that our method can be used as a refinement step after a matching-based methods, and also as a initialization pre-processing before a more expensive localizer, and that we are able to improve the results with different scene representation, such as a texture mesh or even simple raw geometry. Concluding, we show that generic pre-trained features can be transferred to the localization task, thus removing the burden of training dedicated descriptors. We also showed a connection between perceptual and pose similarity, and building on this observation, we proposed a refinement algorithm within a render and compare framework paired with Monte Carlo sampling.